like this, okay? So the point is that we have two independent random variables xi and eta, yes, and we want to understand what is the distribution of the sum, yes. So we already know how to compute this. I mean, we already proved this formula. Now all that we have to do is to have some example, okay? So consider the case when xi has uniform distribution from 0 to 1, and eta also has uniform distribution from 0 to 1. This is one of the problems that we'll have in the problem set, okay? So how do we compute that? Let's see. So we have here that the density of the sum, the point z, would be the integral over r. And now what is the density of xi in the point x? So what function is that? What is the PDF?
PDF of xi?
Yeah, so xi has uniform distribution from 0 to 1.
The function.
Yeah, so what is the PDF?
It's the probability for x being small belongs to 0 to 1.
Well, yeah, not the probability, but the indicator function, right? So, yes, exactly. So we know that if xi has uniform distribution from A to B, then the density of xi in x is just 1 divided by b minus a by the indicator that x belongs to the interval AB. Do we agree? Right? Now, all that I have to do right now is just to, replace b by 0, a by 1, and we get what we want. So 1 divided by b minus a, in our case, will be 1 divided by 1. So 1, right? So all that I have to write is the indicator that x is from 0 to 1. And what's next? So what do I have to write for this? So eta also has... Yes, exactly. So I have to do exactly the same that I have right here, but the difference is that instead of x, I have to write z minus x. Okay? So I have the indicator that z minus x is from 0 to 1 dx. Now, how do I solve this? Any idea? Maybe you know how to solve this. So to solve this, so look, what are the possible values of the indicator function? 0 or 1. So this is either 0 or 1. So we only have two options, right? So what we have to understand is for which cases of x, for which values of x, we have that this is not equal to 0. Okay? So look, the trick is very simple. This is how I solve it, but there are different methods. I think that this is the best one. So we need to find all the possible values for x such that the product that I have right here is not equal to 0. So I have x right here, and x depends on z. So I have to find all possible values, like I have to find for which values of x, depending on z, this will not be equal to 0. Okay? So look, what conditions do we have? The first condition is that x is from 0 to 1. So I have here 0, I have here 1. So by now, I know that I'm over here. Okay? So this is the first condition. X is from 0 to 1. And from here, what do I get? I get, let me do it in a different color. I get that x is going to be what? So first of all, x is going to be less or equal than z. Yes, from here. And also x is going to be greater or equal than what? No. Z minus 1. Yes. So these are the conditions that I have. So all that I have to do right now is to draw the graph of these functions over here. So z equals z. Sorry, x equals z. That would be this. This is x equals z. Here I have the point 1. Yeah. And now the next function is x equals z minus 1. So what function is that? So look, if x equals 0, then z is going to be 1. Yeah. So it will be this function. Here I have minus 1. Here the intersection would be 2 over here. So this is the function, the line, x equals z minus 1. Okay? So look, I obtained the following, that this product right here of these indicators will be not equal to 0 if I'm in the intersection. So the first that I have is that x is from 0 to 1. So right here. The second thing is that x is less or equal than z. So what is that? So this. Yes? X is less or equal than z. Yeah? And I have that x is greater or equal than z minus 1. So this. So the intersection would be this. Let me throw that in a different color again. So this. Okay? So this is the space that I have to consider. All right? So I will have how many cases? Look, I will have 2 cases in total. The first case is when z is from 0 to 1. So case number 1, if z is in the interval 0 and 1, then this integral, then the density in the point z would be equal to the integral. And now look, I have to look, so if z is from 0 to 1, then what are the possible values of x? So look, if z is from 0 to 1, then x is from 0 to z. Okay? So here, 0 and z. And dx. Right? So this is just z. Yeah, right? Now this is only for z being from 0 to 1. Now the second case, case number 2, is when z is from, look, z is from 1 to 2. Then what, the density would be the integral. So what will be the limits of this integral right now? If z is from 0 to 1. From, yes, from z minus 1 to 1 of dx, right? So this would be what? This will be 1 minus z minus 1. So minus z, 2 minus z, right? Yeah. So this is the second answer. I mean, the second case. Otherwise, so the case number 3 is when z is less than 0 or greater than 2, right? When z is right here or here, sorry, not here, but here, then what is going to be the answer for this? 0, okay? That's it. So what is the answer? So look, in this case, we should write the answer like this. So the density, we can write it like this. So we have, first, we obtain z. So we write, this will be z if z is from 0 to 1 plus, so this is the first case, plus 2 minus z if z is from 1 to 2, and that's it, right? Plus 0, okay? So let's draw the graph of this PDF. Look, here we have the graph of the PDF. So we understand that we have to consider the points from 0 to 2, right? So here we have 0, here we have 2. And then, look, from 0 to 1, we just have z. So here we have 1, here we have 1, and we have this line. Yes? And then from 1 to 2, we will have 2 minus z. That is this. So this is z, this is 2 minus z. Otherwise, we have 0. This is the graph of the PDF that we obtained. Now, how can we verify that this is correct? So that actually this is a PDF. So we obtained this result. Now, you don't know the answer. I mean, this is you're in a test, and you want to at least you want to make sure that this is a PDF. Maybe this is not the right PDF that you need, but this is a PDF for sure. How do you verify that this function right here is a PDF?
We can check independently for each random variable.
So
we take p of psi by p of eta for some value, and we should get some value on this line.
sure, we could, yes. That's one option, but that's a very long option. Yes, we need to check the area, right? So we know that the integral from minus infinity to plus infinity of the PDF is equal to 1, right? So here it's very simple to find the integral, because what is the integral in this case? I mean, how do we compute the integral of the PDF in this case? We just compute the area, right? So the area is going to be 2 by 1, right? By half. So it's 1. So everything holds. I mean, at least this is a PDF. Well, this is the right answer for sure, okay?
You also have to verify that the PDF is greater than 0 or greater than or equal to 0 for all values of x, not so?
What do you mean? I mean, this is given, or
Those are I remember you said before that the two conditions were that to verify it was a PDF, that the integral from negative infinity to infinity must be 1.
yes.
F of x for all values of x must be greater than or equal to 0.
Okay, yeah, sure. No, yes, look, here we are not verifying formally that this is a PDF. But actually, we could do that. So, yeah, I understood what you mean. You are right. How do we verify that? So, how can we verify that actually we don't get any negative probability in here?
Because
it's not taking negative.
Yes, exactly, because it's not taking any negative values, right? So we know that the probability that psi belongs to some interval is the integral, right? The integral is going to be negative only if the function itself is negative, right? So if you obtain that the function is negative in somewhere, and for sure this is not a PDF, all right? Okay, good. Now, I think we already discussed why the answer should be like this, right? So why 1 should be the highest point here. I hope we don't have to discuss that again.
If you would like to discuss it one more time.
So look, we have uniform distribution from 1 to 2, from 0 to 1, sorry, and the sum, right? So we discussed that all the possible options that we have for 0 or for 2 are only one option, right? 0, 0 or 1, 1. But for 1, we have many options, okay? Good, so this is how we apply convolution formula. We also, in the seminars, we will find the following. So we need to find the convolution for xi minus eta, the convolution for xi multiplied by eta, and the convolution for xi divided by eta. Okay? So you need to find that by yourself. Okay? Now, how do you compute this? Well, you have to do exactly the same that we did last week, and you need to find the Jacobian of the change of variables that you need, and that's it. Okay? Any questions? No questions, all right.